So today I want to tell you a problem that was devised by a Hungarian mathematician called Paul Turan, and this was something he noticed when he worked in a forced labour camp in World War II. He was actually forced to work in a brick making factory. His job is you had the kilns, right, that's making the bricks, and then he would have to load the bricks onto a trolley, and then he would run that trolley on tracks and take it to the storage units. So you could just run these bricks to and from the storage units. The only problem was when these tracks crossed, because when they crossed, the trolleys had a habit of jumping the tracks and spinning the bricks, right? Oh no, right, what a disaster. So it did make him think, how can we make these tracks, or how can we design this brick making factory so we can minimize the number of crossings? So that's our problem for today. This is the brick factory problem. All right, so we've got kilns and storage units. Let's do one kiln and one storage unit, just to keep it simple. So that's not going to be a problem, is it? So that's just going to be a track connecting the kiln to the storage unit, not a problem at all. What if we had one kiln and two storage units? Doesn't sound like it's going to be a problem either, does it? And then yes, we can just run a track. And we want to connect the kiln to every storage unit. That's the idea. Let's say we had two kilns and two storage units. Maybe that's a little bit more interesting. Maybe we had a kiln here and a kiln there and two storage units. Now we want to connect every kiln to every storage unit. So that would have to connect, that would have to connect, that would have to connect. Maybe you can see I've got a crossing point here. So if I went and connected, I'll just do it. I'm going to have a crossing point. So what do you think? What could we do to solve that problem? So we could have our kilns and storage units like before. We could start to connect them like this, and then instead of crossing the tracks, maybe I'll just do a loop. That would solve the problem. Or as another solution, maybe I could just put my kilns and storage units in a bit of a circle like this. Kiln, storage, kiln, storage. Then I can connect everything together in a loop like that. That's another way to solve the problem. The first interesting example will be 3 kilns and 3 storage units. So let's take a look at that. You connect these together. So far so good, but then we're going to start getting into problems, I think. So I need to connect to the second storage unit, and I connect to the third storage unit. I think I'm going to start getting tracks that are crossing, and I'm going to get an answer like this. I think I have 7 crossing points. Right? Oh, what a disaster. You don't want 7 crossing points. You'll be picking up bricks all day. Right. How could we solve that? How about, I don't know, best solution I can think of, put them in a circle. Let's try that. Kiln storage unit alternating in a nice hexagon. Well, we can connect these up in a nice easy loop, can't we? Okay, so now we've got 6 of the lines. There's 3 more to connect. Essentially, I need to connect the kiln to the storage unit that's opposite on this hexagon. So let's do this one first. That's a nice easy one to connect. This kiln to this storage unit. I don't want to cross that track. I can go the long way around. Nothing wrong with that. And now this kiln to this storage unit opposite. And I will get stuck here. I will have to cross, which is fine. If I go on the outside, I am going to have to cross the track, or if I go on the inside, I'm going to have to cross one of the tracks. I hope that convinces you that I can't do it without crossing a track, but I can do it with one crossing. So that kind of minimizes the number of crossings. And how can we do this in general? Right, so if we've got, let's say, K kilns and S storage units, how can we arrange our factory so that we can minimize the crossings? You might want to have a think about it, but I have an answer for you. I can show you a nice picture that does solve this. Let's have a look. So what you want to do is we're going to try kind of draw it like a graph with an x-axis and a y-axis. I guess a kiln axis and a storage unit axis. So like this, a horizontal and a vertical. I'm going to put the kilns on the horizontal axis. And I'll try and do half on the left and half on the right. Or if it's an odd number, which is fine, I'll do as close as I can to half and half. Well, let's say I've got 6. So I'll put 3 on the left and 3 on the right. So that's going to be my kilns like that. And the storage units I'll put on the vertical axis. And this is how I would lay out the factory. We're going to avoid the origin right there in the middle. That's where we're avoiding. No kilns, no storage units there. Let's say I'll do 5, just so I show you the odd number version of this as well. So 5, I'll do 3 above and 2 below. Yeah, 1, 2, 3, and 2 below. So I'm claiming that this is a minimum. Let's take a look. Let's see what crossings we're going to get. I'm going to take this kiln by kiln. I'll just work my way on the left hand side here, I think. So let's do this first kiln, and I'll connect these 3 storage units up here. No problem so far. Let's do the second kiln. I am going to get crosses here. If I do this kiln to the first storage unit, I'm going to get 2 crosses and connect to that storage unit. Connect to the second storage unit, I've got 1 cross, and then if I connect to the third storage unit, that's not a problem. I can get all the way up. So far, I've got 3. I'll do the final kiln as well. We're going to get quite a few crosses here. Let's try and work it out. I'm going to connect to the third storage unit. It's 1, 2, 3, 4. 4 crosses. And to the next one. 1, 2, and connect. And then to the one at the top, that's not a problem. I can just connect. So I've got another 6 there. So I've got 9 crosses altogether. So I'm going to get 9 on this side as well when I connect these 3 kilns. So on the bottom, we're going to get 3, and we're going to get 3 down here. So altogether, how many crosses are we going to get? 9 plus 9 plus 3 plus 3, 24. Well, I'm claiming that's the best you can do. 24 crosses. That's what we believe that's the best you can do. It's actually not been proven that that's the best, but we haven't found an answer that can do better. We can also write this out as a formula, so you don't have to draw the whole thing. So if you want to work it out, you can work this out as a formula. Same sort of thinking, the way I showed you how it works. If you work it out as a formula, looks like this. Z is the number of crosses. Let's say K kilns S storage units. Then the formula looks like this. K divided by 2. If it's an odd number, you can round that down. Multiplied by K minus 1 divided by 2. If that's an odd number, you can round that down. And multiply that by S divided by 2, which we can round down, and S minus 1 divided by 2, which we can round down. So there's symmetry in this. I guess there's no difference really between the kilns and the storage unit, not from a mathematical point of view. So you can see the symmetry in there. We can just double check our result.
Let's do it.
What did I have? 6 kilns, 5 storage units. So that's going to be 6 divided by 2. We might have to round that down. That's going to be 5 divided by 2 and round that down. Storage units, 5 storage units, so that's now a 5 divided by 2, round that down, and 4 divided by 2, round that down. 6 divided by 2 is just 3, multiplied by, this is 2.5, we round it down to 2, same here, 2.5, round it down to 2, and this here, that's just 2, that's fine. 3 times 2 times 2 times 2 is 24, which is the answer we've got. So that is a formula that describes this picture. We think that's the minimum. Not proven, but it does mean that your number of crosses, if you're in this situation with your kilns and your storage units, is going to be this number or smaller. We know that much. So it's this number or better. We think that's the minimum.
I can't believe people aren't all over this one. I can't believe it's not like been cracked.
Yeah, so they did think they proved this at one point, and that was a proof that people accepted for 11 years. It's one of those stories when they go, oh yeah, that seems right, until someone noticed a mistake. We know this much. So this minimum number of crosses, it's going to be less than my little formula and 83% of that. So we're whittling it down. We're sandwiching it between these numbers. We're getting there. We're trying to hone in on that number. It has been proven for some numbers. So it's been proven for number of kilns less than or equal to 6, and storage units as many as you like. So arbitrarily many storage units and 6 kilns or less, we know that is the minimum. So that has been proven, or vice versa, because it's all symmetric if you want to do it the other way around. But for any values, no, we haven't proven that that's the minimum yet. And there is applications for this apart from building bricks. Yeah, you want to use this kind of idea when you're making computer chips. So you've got your circuitry in your computer chip and you don't want them crossing, you want to minimize those crosses, because every time those circuits cross, you have to do that in a new layer so that those circuits don't cross. So it's important when making things like that. It might be worth talking about complete graphs as well. A complete graph is the idea where you have these dots. They're not kilns and storage units anymore. They're just dots, and you want to connect everything to everything else. So if I had like 5 dots in a pentagon and I would connect everything to everything else, first of all I could just connect my pentagon up and then connect all the other lines I haven't done yet. So that's called a complete graph because you've connected everything to everything. That's got 5 crossing points on it. Can we minimize that? Same question. So can we minimize that? Yeah, you can. So we could have the 5 dots in a pentagon, like that, and we can draw that out as a pentagon as well. So let's do our other lines. So we could have one line there, we could have one line there, I think we could have one line sort of going out on the outside like that, one line going on the outside like that, and what am I missing? This point to this point I'm missing, and I have to cross. Yeah. So I do have to cross at one point. So that's me minimizing the number of crossings. So I can get it down to 1. So the question is, how do you do that in general? And that's connecting everything to everything. We think we've got an answer to that as well. It's a really nice answer, actually. I'll do the 6 version for this. So if I wanted to connect everything to everything for 6, you draw it as a regular polygon. So I'm going to draw a hexagon out. I then draw in my edges. There you go. And now I need to draw in the remaining lines. This is the rule. If the slope is positive, it goes on the inside of the polygon. So positive slope, I mean something like this, that has a positive gradient, because it's sloping upwards. This line has a positive gradient, so it stays on the inside. And this line has a positive gradient, it stays on the inside. Oh, and I should say, this line is also positive, going vertically up, and this line going vertically up is also positive as well. If your line is 0 or negative, it goes on the outside. So this point to this point would be negative, a negative slope. So I'm going to draw it on the outside instead, like that. And this point to this point would be negative, so I'm going to draw that on the outside as well. This point here to this point. So I've only got one line left. It's this point connecting to this point, which would have been your 0. And that's going to have to cross on the outside. There. How many crosses do we have? 3, actually. There's 2 there on the inside. And then there's 1 there on the outside. And that, again, is what we think is the minimum number of crossings for that. You can write that out as a formula as well. So if you just have n points connecting everything to everything, for this diagram, this is how many crosses it has. It is 1/4 of, and then we do a rounding down of n divided by 2, round down n minus 1 divided by 2, round down n minus 2 divided by 2, round down n minus 3 over 2, like that. I did 6 here, didn't I? Quarter of 6 over 2, rounding down, 5 over 2, rounding down, 4 over 2, and 3 over 2. So it's going to be 1/4 of 3 times, that's going to be a 2, that's going to be a 2, and that is 1.5 rounded down, which is a 1, which is going to be, 3, which is exactly what it should be. So that formula is describing that picture, and we think that's the minimum. Again, it's the same problem. We haven't found a drawing that is better. So we think that's the minimum. And that's useful to know because that's kind of your worst case scenario, because it's everything connecting to everything else. So if you've got a graph which doesn't connect everything to everything else, it's going to be that value or smaller than that value. So it's worth knowing that as well. We have proven that it is a minimum for n less than or equal to 12. So we do know it's a minimum for that, but for the other numbers, still a conjecture.
If you enjoy learning stuff here on Numberphile, well, you're going to love Brilliant. Their custom-made courses, questions and quizzes will expand your mind and bring a few smiles to your face as well. Everything's so interactive, meaning you don't just look at a screen, you get hands-on with the material, and there's no better way to learn than that. I don't just enjoy the knowledge on Brilliant, I like that it has a bit of personality. Sometimes it's quite funny. This course on math history, well, it's a favourite of mine. And by the way, Brilliant has a 30-day free trial, so you could go and do this course right now. And if you do sign up to their annual premium subscription, there's a 20% discount by visiting brilliant.org/numberphile. It's never too late to learn something new. Check out Brilliant. There's also a link in the video description.
For us to be all related to the same ancestors. Now you were saying this is not true to life, and I agree, this is not true to life, because in this example, I'm just as likely to have 2 parents who are from Paris